All right, this is Math 2321, Calculus 3. Okay. Now, since people are slowly getting in, let me just start by quickly going over the syllabus, and then we will get going there. So people who are online, please make use of the chat option to communicate with any questions or answers or any issues. Okay. So before I do that, can you hear me, all of you, or just unmute and say yes? All right, good. Can you see what is there? I mean, there is a black board which is blank, and there's a screen which is blank. Can you see all of that? Or okay, let's see. Fine. Can you hear it better now? I mean, there is a fan going on here, so that might be part of the extra noise you might be hearing. Okay, but okay. You can increase the volume, but that might make it more uncomfortable for people sitting in this room. So, can you hear better now? Okay. All right, so let's start by sharing the screen with my syllabus, and then for you, you can see there. Okay. This one, let me share. Okay. Nothing new. I mean, I'm hoping that all of you got a chance to take a look at the syllabus. Okay. My office hours are Monday, Tuesday, Wednesday from 12 to 1. I'll post the Zoom link in the announcement section of Canvas maybe today. Okay. I'm still trying to figure out some logistics. The textbook is what if you took Calculus 2 here, you probably used this textbook at the end of the semester. But if you did not take Calculus 2 here, you might want to purchase this textbook either electronically or paper-based. It's up to you. Okay. If you buy the electronic version, the good thing is that it comes with its own lectures for each of the sections and also some of the homework solutions. Okay. So that's the incentive with the PDF online version in addition to producing the paper. So I'll post any useful material on Canvas. I'll show you what exactly and where to look and so on. Okay. I think all of you are probably interested in knowing what the grading policy would be. We'll have 3 tests that will be one at the end of each chapter, right? So when we finish chapters 1 and 1 is actually a review chapter. So chapter 2, we will have 1 test, chapter 3, another test, and chapter 4, another test. Mostly that is how we do it in summer. Okay. The typical grading scheme of 93 being an A and so on. The rest of the things here are mostly, things that you know. There is a teaching assistant for this course. He has office hour separately. So if you cannot make it to my office hours, or if you want a separate person helping you or more friendly person helping you, okay, that is the Zoom link for the TA. And the course coordinator is Professor Sumi Siu. If you have any complaints about me, you could talk to her or to the teaching director. Okay. You can always talk to me first, but if you think that that won't help, you can always go upstairs. I would prefer talking to these instead of going up to the university president and complaining that Calculus 3 is not going well. Okay. Instead of going all the way up there, try to start at lower levels. Okay. And hopefully we will try to sort out the problems. And if you raise anything with one of these, usually they are anonymous, so I won't know who is complaining. We'll try to sort it out. All right, the registrar's dates, the last day to drop and all that stuff is here. Okay. And you can read all these things at your leisure time. Those are all nice things to read. Okay, now in terms of the course content, This is a very fast moving class, especially in the summer. Okay, so the main chapters we are doing, chapter 1 is mainly a review chapter, okay, especially the first three things that I have highlighted there. Those are mostly done during calculus 2 here, but I will go through that anyway because you may have forgotten it. Okay, we need that stuff later, but the main thing starts from here onwards. Okay. So the end of chapter 2, you will have one test here, then going down the end of chapter 3, you have another test. Okay, all these tests are of 100 minutes duration, which we'll be doing separately on Thursdays. And the last test is going to be based on the vector calculus part. Okay. And I think we might schedule it during the final exam period so that you get some time to study, because that is the more difficult part of the semester. Okay. So the calculus 3 typically starts off at a very slow rate and kind of quickly picks up speed, and at some point you will find it really unbearable. Okay, that is around here. I don't want to scare you, but you have to be just make sure that you don't fall behind. Okay, that is what is important here. All right, now in terms of what you will see on Canvas, I've kind of limited it to very few items here. Okay, this is probably what you might be seeing. So if you go to modules, this is where most of the things that you need for the semester are. Okay, so you can see that I'll post some worksheets for every lecture. Okay, we won't probably need any worksheets for today's lecture. It's a very basic level review, but from tomorrow onwards, we'll be making use of these worksheets. I won't post the solutions for this separately, so you have to attend the lecture either live or recorded to get the answers for this. So I have written that here clearly. Okay. So we will go over all these problems during the lecture, but I'm not going to separately post answers to this. So there will be a worksheet for all the important topics we do. And you will see that if you stay on top of these worksheets, you will be in very good shape for all the quizzes and tests. Okay, so you don't have to go do extra research on Wikipedia to find out what calculus 3 is about. Okay. And I think there are probably 2 or 3 students who still haven't taken the survey to schedule your quizzes. I think you know who you are. Okay, so please just go there, and I think I locked it at 8 o'clock, but if you cannot get it, just I can probably extend the time to 8 o'clock today, and you can pick a time for your quizzes. Right now, I don't know who all took it or who don't, so just do that. I think there are 2 more students remaining. Okay, so you know who you are. Let me just. So if you haven't finished it, you have time till 8 o'clock tonight to just do it. It takes only 30 seconds to do it. So please. Okay. All right. So I can stop sharing the screen and ask you whether you have any questions about the course or any logistics. Any questions? It's a very small section, so you shouldn't feel bad in just unmuting and speaking. Okay, so it's probably the smallest section I have taught in a long time. So I'm kind of happy that I have a small section. Okay. So feel free to unmute and speak or type in the chat window. Okay, nobody is going to judge you if something is wrong or. Okay. Any questions about anything? All right. So today we will just do some very basic stuff. Okay. So let me just talk about what we're going to do this semester. called calculus 3, but if you ask most people, they will say that this is also called multivariable calculus or vector calculus. Okay. So all the calculus that you have done so far in calculus 1 and 2, just single variable calculus. Okay. You are mostly on a straight line. You had some y equal to f of x. Okay. So you have a dependent variable y that depends on an independent variable x, and you are doing all kinds of things with this. Okay. That is what your calculus 1 and 2 we're doing. So this semester we're going to increase the number of variables to 2 or more independent variables. Instead of saying that the area of a circle depends on the radius, okay. Now, if you can see things like this, pressure is a function of both temperature and volume. Okay, so there are two variables here. Okay, so instead of talking about pressure as a function of temperature alone, we can talk about two independent variables. That is what the multivariable part is. Okay, that also makes the understanding of these functions more complicated because now we are living in higher dimensions. Okay, and that is where vectors are useful in understanding those things. So it kind of goes hand in hand. Whenever you're talking about higher dimensions, you need vectors to deal with those things. Okay, so that is why it's called calculus of vectors or vector calculus. Okay, so that is what we're going to do. So we have three main components here. We have derivatives of multivariable functions. Okay, that is what we'll be doing in chapter 2. Integrals of multivariable functions in chapter 3. And then we combine these two. Vector calculus in chapter 4. That is where we see the connection between these things and what you probably might see in physics 2, in electricity and magnetism, or in fluid mechanics and so on. Okay, there's a lot of similar things that you would see here and there. Yeah, that is all happening in vector calculus. Speaking of derivatives and integrals, all I need you to know at this point for this course is basic calculus. Okay. You don't need to know fancy things. Okay, so you need to know how to find the derivatives of very basic things, and similarly integrals of very basic things. That includes U substitution. I don't care about the integral of secant inverse of. I really don't care about this. Okay. But I do care about more basic functions like e to the power of x or sine x and cosine x. Okay, so my expectations from calculus is very minimal, but you should know that. Okay. Everything else will follow from what we do. So don't worry about if you don't know what vector is, we'll learn it. Okay. Okay, so that is going to be our course objective. And in terms of the level of difficulty, you would see that this week it kind of goes like this. And then 2 weeks it kind of slowly goes like this. And then it kind of quickly kind of gains pace. And in terms of level of difficulty, okay, so this is around the end of chapter 2. Up to there, things are kind of peaceful, and then it suddenly shoots up, and that's where we just need to be making sure that you don't fall behind. Okay, that's all you need to do. Just stay on top of the course, do your homework, master the worksheets, you'll be okay. All right, so those are my expectations, and please feel free to reach out to me by email or through Canvas messaging if you have any questions about the course. Okay. So let's start with section 1.2. Now the title of this section is rather fancy, but we just need some very basic things out of this. Okay. Rn as a vector space. But don't be scared with the title. We're not going to talk about vector spaces here. So what we need here is some basic notations and definitions. Okay, not going to spend a lot of time on this one, okay, because there's a whole lot of information in the textbook. So that is why attending the lectures either live or recorded, it's important, because you need to filter out some of that information in the textbook, okay, and not get lost in the jungle of all the technical stuff. All right, so we usually use this notation here, this script R, for the set of all real numbers. So it's a number line that you have probably seen in your school days. Okay? So all the numbers that you know of, which are real, are lying from left to right, from negative infinity to infinity. Okay, so that has got rational numbers, irrational numbers, integers, you name it, everything. Okay? If you take any two numbers here, say A and B, doesn't matter where it is. Okay, so maybe 0 is here. Then the distance between those two, distance between A and B. So this is how we slowly develop the concept of distance. Okay. Now that's not too difficult, right? You take a ruler and measure it. Okay. Or you could just subtract the two numbers and write it as A minus B or B minus A. Now you might say, well, if you do one of those, it's going to be a negative number, right? And distance cannot be negative. So the way to denote this, whether it's positive or negative, is to use an absolute value and write as the absolute value of A minus B. So that way we don't have to worry about whether it's positive 3 or negative 3, right? Distance is just one number. So that's a very simple concept. If you have just a line, that's a distance. Now we're going to the next thing that you can look from a real number. It's going to be an ordered pair of real numbers. If you take the XY plane, that is what we represent as R2. Okay, the 2 here stands for the dimension, right? It's a two-dimensional plane. So if you take a piece of paper and draw something, that is a two-dimensional plane. Okay. So all of you know this. You have been drawing graphs from your middle school. You take a piece of paper, you typically name it as X and Y like this because that's a convention, right? If tomorrow, if you want to name this as X-axis, that is a Y-axis, it's not wrong. Then you have to change all the textbooks. Okay? So now that we are used to this notation, we call that as X, this is Y. And if you pick any 2 points here, say, let's call this as X1, Y1, and be more general, this is X2, Y2. Okay, so remember that anything in R2 needs 2 coordinates to represent its position, needs an X coordinate and a Y coordinate. Okay? So you got 1 point here, 1 point there. Let's name this as P, this is Q. What is the straight line distance from P to Q? So if you call this as D, what is D? Well, that's not too difficult to kind of draw and figure out, right? So this is X1, Y1. And if you draw a line from this point directly downwards, the foot of this point would be X2, Y1. Because this is translated from X1 to X2. It has not moved up or down, so the Y coordinate is still Y1. Okay. So that's what you have. And the length of this line, or the distance between this and this, is the absolute value of x1 minus x2 or x2 minus x1. Okay, just like what we did there, because it's on a straight line. Okay. And since the y coordinates are the same, the length of this is just the difference in the x coordinates. And similarly, the length of this line is going to be absolute value of y1 minus y2 or y2 minus y1. That's because the x position has not changed. And you know some theorem from your high school that tells you how to find the hypotenuse of a right angle triangle. Okay, so use Pythagoras theorem. And you have b equal to the square root of the length of the base square plus the length of the height square, right? So it's going to be, now that you are squaring it, we don't have to worry about the absolute value. So it's going to be x1 minus x2 whole square plus y2 minus y1 minus y2 whole square. Okay, at this point, all of you know that it doesn't make any difference if you write x1 minus x2 or x2 minus x1. This is the simplest physical thing you can talk about, right? The distance between two things. Okay, so whether it's on a line or it's on a plane, you can always give a mathematical definition to that concept of distance. Okay. So what is the point of going from this to this? Now we can expand our imagination into three-dimensional space. Okay, so into R3, which is your XYZ. So we need three axes now, three coordinates, okay, because now it's something in space right here. First thing, we need a convention, right? Because you have three axes, who is going to decide what is what? Okay, that is what mathematicians do. We have to fix something so that everyone agrees on the same page and then don't worry about who is looking at it, right? Our notation is this. This axis, which is coming towards you, okay, that is the x-axis. This is your y-axis and this is your z-axis. Now, if you go and talk to somebody in the physics department, they'll say, no. We'll keep our x, y like this, like we used to do, and we'll keep z coming towards you. Okay. There's nothing wrong or right about this. It's all about what you want to do. Okay. This is going to be our convention. This is called the right-handed system. It's called the right-handed system because if you keep your xy plane to be your thumb, your right hand like this, okay, the thumb is pointing in the z-axis. The thumb of your right hand is the positive z-axis. That is what we're going to follow throughout our textbook. Okay, so if you want to change this, it's not mathematically wrong, but we have to change a lot of other things. Okay. So this is our convention, the right-handed system. So if you take a physics course where they use a slightly different system, you have to kind of keep switching back and forth. Okay. So if you are given 2 points here, so x1, y1, z1, and x2, y2, z2, what is the straight line distance between these 2 points? Can you expand or can you kind of extrapolate from this formula here and write a similar expression here for the distance d without going through a whole bunch of crazy pictures and writing all that stuff? Can you just tell me what it is? Yes, yeah. Yes. So there will be an additional term, right? So it's going to be the square root of x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square. Just make sure that the square root covers everything. Okay. This is as far as we can imagine, right? We live in a three-dimensional world. Okay, if you ask somebody to visualize things, they could visualize in R3. The 3 stands for 3 dimensions. Anything beyond those becomes more difficult to picturize and draw, I think. Okay, so if you talk about R4, R5, those are mathematically possible because you could have a problem with 4 variables or 5 variables. Okay, but then to draw it is not easy. Okay, in fact, it's impossible after 4. 4 you could kind of draw and make people convinced about, okay, that is R4. Okay, things from here on you cannot even draw it. Okay. But the concept of distance is going to be the same. You just keep on adding more terms. So this is for R3. R4 will have a 4th dimension here. R5 will have a 5th dimension here, and so on. Okay. So that is how the idea of distance kind of develops from a straight line to a plane to space. Okay. So that is kind of nice way of progressing through from a single dimension. All right. Any questions on distance? So there's nothing fancy here, right? All of you have seen this before. Just wanted to remind you of this. We'll just quickly mention a couple of things about these two rather fundamental formulas of geometry. So based on this here, what will be the geometric name for the curve generated by the point P, which is the same distance R let's call it little r, okay, from a given point x1, y1. I think all of you know the answer. I mean, I wrote a long question there, but I think I know the answer to this. What is that thing? It's a circle, right? So if you're given a point x1, y1, then the set of all the points which are the same distance around it, I drew it dashed because if I try to draw a circle, it won't look like a circle. Okay, so dash one, at least I can claim it looks like a circle. Okay. So this distance is r. So the distance r equal to the square root of so let's call this point P to be equal to so it's x minus x1 whole square plus y minus y1 whole square. So the point P is your xy because it's moving all around the circle. Okay. P here, P here, P here, and so on. Okay. That is your x and y, and its distance to the point x1, y1, which is at the center, is always preserved at r. Okay. Now, if you square this, you probably have seen this equation, x minus x1 whole square plus y minus y1 whole square equal to r square. Okay. This is what you call as the standard equation of a circle with center at the point x1, y1 and the radius equal to r. Okay. You should be familiar with this equation later in chapter 3 when we do polar coordinates. Okay. This is going to be the basis for polar coordinates. So if you're given a circle in R2, you can always write an algebraic equation that represents all the points on that circle if you know the center and the radius. Okay. And in particular, if the center is a point 0, 0, we get x square plus y square equal to r square. This is going to be our base equation for polar coordinates in chapter 3, so please don't forget this. Okay. Look like a very trivial concept, but this is how we develop things in math. Start from the scratch and then slowly build it. Okay. Any questions on this one? This is pretty straightforward, right? Now let's go to R3 and ask the same question. Okay. Sorry to recycle this. What will be the geometric name for a curve or for the surface? And now we should be able to stand on it because it's an R3. Okay. You cannot stand on a circle because it's on a plane, right? Now we should be able to stand on it, maybe move on it. So what is the geometric name for the surface generated by P, which is the same distance R from a given point x1, y1, z1? What do you think is the three-dimensional cousin of circle? Yeah, a sphere, right? And it's the best three-dimensional picture or three-dimensional surface you can talk about because it's symmetric everywhere. Okay. There is nothing which is perfectly a sphere. Okay. People talk about Earth being a sphere, but it's approximately a sphere. Okay. If you want it to be a perfect sphere, that's very difficult. It's a mathematical idealization that you talk about everything being perfectly symmetric with respect to. But Earth is more or less a sphere, okay, not flat. All right, so that means in terms of the distance we did, we have one more term here. Okay. And that is using the three-dimensional concept of distance. We have the same distance on all the sides. And if you square it, you get x minus x1 whole square plus y minus y1 whole square plus z minus z1 whole square equal to r square. Okay. Again, you should see the similarity here. The circle, it was one-dimensional less. Okay. So all that was missing was the z part here, right? You bring the z in, it goes in dimension from R2 to R3. Okay, just a different name now. So not only that, you can also stand on it if you want. Okay. This is what we call as a standard equation of a sphere with the center at x1, y1, z1, and the radius is r. Okay. Standard equation of a sphere. With center at x1, y1, z1, and radius equal to r. So of course, the next question is, what happens if the center is the origin, which is 0, 0, 0? Okay, it collapses into a much more easier equation. So 0, 0, 0. This becomes x squared plus y squared plus z squared equal to r squared. Okay. Again, we need this later when we do spherical coordinates in chapter 3. This is where we will start. Okay. We might use a slightly different Greek letter to represent the radius, but that doesn't change the meaning. Okay. That's just for convenience purposes. So going forward, please don't forget about the circle and the sphere, okay, especially the algebraic way of representing this. And that is the beauty of algebra, that it can give meanings to things that you probably draw on a piece of paper. Okay, there is a meaning to that in terms of letters that you write. Okay. Any questions about the distance formula or this one? All right. Now that we know the concept of distance, and since we are going to live in higher dimensional worlds in this course, okay, let's now talk about or focus on points in a plane. Okay, so let's talk about R2, and let's take 2 points here, P and Q, and draw a line segment from P to Q. Okay. You could go from Q to P, but I'm trying to stay from P to Q. So my direction is important here. Okay. So definition, vector is a physical quantity and I'm pretty sure you have seen this either in calculus 2 or in physics 1 or statics or a lot of places where you would see this. Even biologists deal with vectors, but that's a different kind of vector. Okay. But R vector is a physical quantity with what are the two things that a vector needs? Magnitude, which is a number, and it should tell you from where to where the direction, right? With the magnitude. So if you talk about just the speed of an object, that is just the magnitude, okay, and the direction. I think the most famous example for a vector is velocity, acceleration, okay, because it has 55 miles per hour going northwest, okay, that is a velocity, just 55 miles per hour is speed. Okay. So something that has only got a magnitude is called a scalar. And we can live with that in when you're talking about a straight line problem. We don't have to worry about vectors, but once we go into higher dimensions, we also need to worry about in which direction you're moving. Okay, so that is why we need vectors here, and in particular, the vector that tells you the relative positions of each other. This is called the displacement vector. Okay, so they're going from P to Q. Okay. So the displacement vector from P to Q. Okay. There are different ways of writing it. You can write this PQ with an arrow. Okay. Some textbooks use some kind of a lowercase letter with an arrow. Okay. Or U. It's how much you have traveled from P to Q. Okay. So it's going to be equal to Q minus P. So the coordinates of Q minus the coordinates of P. Okay, I'm pretty sure all these things are pretty obvious to you, but I'm just trying to make sure that all of us are familiar with these terms. Okay, so for example, if you had, say, 1, 3 as P and Q as 3, 7, then the displacement vector from P to Q, okay, if you call it as U, would be 3, 7 minus 1, 3. Which is 2, 4. So a vector in R2 has got two of these things. Okay? This is what you call as the two components of the vector. So you call coordinates for a point, components for a vector. Okay, mean the same thing. So there is a displacement vector, okay, but it doesn't tell you how much distance you have traveled, right? So the magnitude of the vector U in general, if it is say AB, is given by, some textbooks write it like this, okay? So don't read it as absolute value, it's the magnitude of U. Or you can also use double vertical lines. And that's just equal to the square root of a square plus b square, okay, because you're just using Pythagoras theorem. So A is going to be the component here, and B is going to be the component there. Okay, so it's a square root of a square plus b square. So it's just a distance formula, right? There's nothing fancy going on here. You're just taking the distance of this line, which is going to be this difference between this minus this square plus this minus this square. So if you take the distance between PQ, it's going to be the square root of 3 minus 1 whole square plus 4 minus 3 whole square. 7 minus 3 whole square. If you use the distance formula, which we did a few minutes ago, right? And that is exactly what is going on here. The square root of 2 square plus 4 square, which is the square root of 16 plus 4, which is 20. So if you're given a vector in terms of the components, you could find the magnitude, which is the sum of the squares taking the square root. Okay. And I hope all of you know that this is not equal to a plus b. Okay. I hope things like that won't be an issue in this course. Okay. You never know. Sometimes you're pushed to a corner and you will start believing in these kinds of mathematical silly things. Okay. So what about vector u equal to u1, u2, u3 in R3? So there are 3 components now because it's an R3. Okay. What is going to be the magnitude of u there? I'm using subscripts because it's convenient. You could write ABC if you want. Okay. How do you write the magnitude of u here? Yeah. Yeah. So it's again, let's say sum of the squares. Okay. Don't forget to take the square root because otherwise you're going to get the square of the length. Okay. So make sure that you take the square root. Again, it's in agreement with the Pythagoras theorem, but now it's an R3. Alrighty. There is a very important concept which, when you look at the first time, you might think, oh, what is so big about this? Okay. But it's something we need later in multiple places. So please write this down carefully. So if u is any vector, when you say it's any vector, which means it has got some length. Okay. It could be some finite length, but it should not be equal to 0. Then a unit vector is a vector in the same direction as u with length or magnitude equal to what? And people online try to fill this answer. Equal to 1. The word unit stands for 1. It's a very special vector because it helps us scale vectors of arbitrary length into length 1. Okay, that makes us kind of suitable for other applications where if you want a vector of length 5, first scale it down to 1, then multiply by 5. Okay. So if u is any vector, whether it's an R2 or R3, we don't care. Okay. Could have 2 components, 3 components. Then if you want to get a vector along the same direction with length 1, okay, that vector is called a unit vector. Now, how do you find a unit vector for a given vector? Do you remember? Yeah. Yes. So he says that they divide the vector by its magnitude. Okay. So to get a unit vector in the same direction as u, just divide by its magnitude. That is why I did the magnitude first, because now I can use it here. Okay. So unit vector in the direction of u can be written as u divided by the magnitude of u. Of course, assuming that u is not a zero vector. Okay. Some textbooks use a different notation for this. Okay. We don't. Our textbook has some notational things you have to get used to. Okay. There is no special notation in our textbook. If you're a physicist, you might see things like this. Okay, they have a hat, right? But we don't have it. So we'll just talk about a unit vector just like any other vector. But if you're a physics major or somebody who does a lot of physics, okay, then you might put a hat. I don't care which way you do it. The important thing is that this vector always has a magnitude of 1, okay, and that is what qualifies it to be a unit vector. How do you get a unit vector in the opposite direction as this vector u? Not a trick question, you know. What simple change will make it the opposite direction? Can people online try? Don't have to use any theorems or anything. If you're given a vector, how do you negative, right? So just negate the vector and you'll get the vector. So negative of u over the magnitude of u would be opposite to that vector. So if one is going this way, the other one is going this way. There's a unit vector opposite to the direction of u. This is something that we will see later, that for every vector, we can always talk about a vector opposite to it just by negating it, right? All right, so we talked about a vector in R2 and R3. We talked about its magnitude and what it means by a unit vector. Okay, let's do a quick example just to kind of make sure that all of you understand this. Okay, nothing fancy. I'm going to give you a vector, or I'm going to give you 2 points in R3. I'm going to ask you to find a displacement vector and a unit vector. Okay, so let's do that. Still very early days in calculus 3. So example, let p equal to 2, 3, -5, and q equal to -1, 3, 7 be 2 points in R3. It's in R3 because it has got 3 coordinates. So question 1, find the displacement vector u equal to pq. And question 2, write a unit vector in the same direction as u. All right, so just take a couple of seconds maybe to do it. All right, so PQ, since we have defined it from P to Q, okay, must be Q minus P. So U equal to Q minus P, and that's going to be equal to negative 3 minus 3 is 0, and 7 minus negative 5 is 12. Based on the numbers I gave you. Now, the second question is asking you for a unit vector, so you might also want to just find its magnitude because you need this. Okay. So the magnitude of U is the square root of negative 3 square plus 12 square, which is the square root of 153. And you'll see that in this course, I'm not particularly excited about finding what that number is. Okay, you can just leave it as square root of 153. That's okay. We have bigger things to worry about in this course. So don't take a calculator and try to write the answer to a million decimal places. That's not what we are trying to achieve here. Okay, so that is fine. So the answer to question 2 would be then each of these components divided by its magnitude, right? So a unit vector in the direction of U would be negative 3 divided by the square root of 153. 0 divided by square root of 153, that's just 0. And 12 divided by square root of 153. Now, I don't care if you write it like this or 1 over square root of 153 times negative 3, 0, 12. That's okay. What you don't want to do is, somehow start with a vector in R3 and end up with a vector in R2. Those things are illegal, okay? So even if this is 0, you still have to write the 0. So you don't have to. So this is not, don't try to do any favors by reducing its dimension to 2. Okay. Those things can get you in federal prison sometimes. So please don't do it. Okay. So as long as you maintain the dimensions of the vector intact, you're okay. All right, so that is just kind of a silly example, but any questions about finding the unit vector? I don't want you to be haunted by this later in chapters 2 and 3. Okay, that's why I'm doing it now. Oh, other things which you would see in the textbook if you go through chapter 1.2 are just some basic operations with vectors. Just quickly go over that. So first of all, some students like this one, the alternate notation for vectors. If somebody is kind of calling you at the middle of the night and asking you, give me a unit vector, what will be your most natural unit vector? Some people can just call you at the middle of the night. Hey, give me a unit vector. What will be your? It's not 0, 0. Well, so let's try about other nice vectors. Just try. 1, 1, 1 looks like a unit vector. Probably meant it has to be of length 1. Okay, so 1, 0, 0. Okay, let's start with R2, right? So he went to R3 first. That's okay. We'll come there. Tell me a nice, easy unit vector in R2. 1, 0, right? It's on the x-axis. So if you just go from the origin to this point, that is the easiest unit vector you can travel, right? Distance 1 from the origin. Okay. Physicists give it a special notation called I. Okay. So they also put I hat. Okay. So instead of writing it as 1, 0, you can just as I. Similarly, on the y-axis, this is x-axis here, y-axis here. Okay. At the unit distance of 1 from the origin along the y-axis, this is j, and this is 0, 1. So if you talk about a vector u equal to 2, 3, okay, this is the same as writing 2i plus 3j. So when you do these things in probably statics or something where you are defining the position of something in R2 or R3, you might use these ij notations there. Okay, it's the same thing as what you just did. So an x component of 2 and a y component of 3 has an I component of 2 and a j component of 3. Okay, so same thing. Okay. And the magnitude of this is still going to be the square root of 2 square plus 3 square, which is the square root of 13. Okay, so that shouldn't bother you, okay, whether you write it in the component form or the ij form. Okay, they are the same vector, and everything else that comes out of it will be the same as well. And what Faisal wrote there is the unit vector in R3. So if you take unit vectors along the x, y, and the z axis, so we have a unit vector along the x-axis, which is going to be 1, 0, 0. The j vector, which is 0, 1, 0, and the k vector, which is 0, 0, 1. And if you are a physics major who is very religious about symbols, I hope I'm not offending you by writing arrow and not a hat there. Okay, same thing. So any point here, say P equal to 3, 4, 5, it's the same as writing 3i plus 4j plus 5k. You're free to use whichever notation is easy for you. I don't care. Okay. Such things should not be the reason why you're not doing well in calculus 3, or I don't like this notation. So both notations are equally correct and equally acceptable. All right. Basic properties of vectors. And for writing these properties, it's okay to take vectors in R2 or R3 or any dimension as long as they are in the same dimension. Okay, so let's take U, V, W, B, any vectors in R2 or R3, I don't care. Okay. The difference is this has 2 components, there has 3 components, but in terms of the properties we're going to list, it shouldn't matter. And let K be any scalar, which means any number. So property 1, if U equal to U1, U2, U3, and V equal to V1, V2, V3. Okay, so let's take R3 for example. Then U plus V is also a vector in R3. Well, if you've never seen this, and if I ask you how do you do this, your intuition tells you that you just add the components. Okay, that's true. This is just U1 plus V1, U2 plus V2, U3 plus V3. That's a nice thing if you know the components, right? You can just add them together and you still get a vector. Okay, it shouldn't end up with a number. That is when things go wrong. You have 2 vectors in R3, you still get the vector in R3. The same thing with the subtraction. All these would be minus, minus, and minus. Property number 2, again, this might be obvious once you see it, like, oh, I would have done that, anyway. Right? Property 2, for the scalar k, k times u. Okay, let's keep u as u1, u2, u3. In case a scalar, what do you think it's going to do? If you've never seen this, what does your intuition tell you? It's going to do what? people online, you want to tell me, what do you think multiplication by that k is going to do to this vector? Just going to multiply each of the component, right? Yep. So it's going to be k times u1, k times u2, and k times u3. In other words, the vector is scaled by a value of k. That is why it's called a scalar, okay, because it's getting scaled. So this is u scaled by k, which is a number. If k is 1, it doesn't do anything, but if k is not equal to 1, it's going to do some kind of scaling. It's going to either go longer, shorter, or go in the opposite direction. So for example, if you take this to be your u, this is your x, y, z axis. All of you know what it means by saying 2 times u, just twice the length. And if you say negative 1/5 u or negative 1/2 u, okay, that's going to go opposite, but it's going to be half the length of this. It's not drawn to scale. So this is negative 1/2 u. Okay, so the sign here tells you in which direction it's moving, and the number itself tells you whether it's going to be stretched or kind of squished in terms of its length. Okay. So if k is greater than 1, it's going to get elongated, and k less than 1 means getting it shortened. Okay. The more fancy words will be stretching and compressing, and if k is negative, it's going in the opposite direction. Those are the two main properties of vectors in terms of adding and scalar multiplication. Okay. So adding two vectors will give another vector, and multiplying a scalar will give you another vector which is scaled by that particular value. Okay. The other properties which you usually see in textbooks are pretty intuitive. Okay. So property 3, u plus v equal to v plus u. Okay. It doesn't matter whether you do vector 1 plus vector 2 or vector 2 plus vector 1, you get the same answer, okay, because you are just adding the components of vectors. Okay. Adding two numbers is always going to satisfy this. This is called the commutative property. But don't take things for granted in higher level math. Okay, there you will see a few things which are not commutative. So, when it is commutative, that's pretty useful. Okay. U plus v plus w equal to u plus v plus w. I know you have seen this in middle school or high school. What do you call this property? Any answers online? Associative property, right? It's okay if if you've forgotten it. And if you have k times, oops, no vector here, k times u plus v, that is equal to k times u plus k times v. Every time you define something new, we list this property so that we can do these things taken for granted. Okay. That's why even if you are like, oh, I know that anyway. But it's always nice to define this clearly so that you don't have to keep doubting what you're doing. What do you call this property? Distributive property. Okay. So all these properties are still true. Please note that I have not talked about multiplying two vectors. Okay, that is a different creature altogether, right? All I've talked about is adding and subtracting two vectors, and also the commutative, associative, and distributive properties of vector addition, right? So at this point, that's all you know. Okay? If you ask me what is vector u times vector v, that's a complicated question. which we will soon answer, but that needs more conceptual stuff. All right. Any questions on these? This is what section 1.2 is about. I told you there's nothing heavy there, but if you've never seen a vector or if you forgot things, it's a time to just refresh your memory. Okay. One last thing in section 1.2, two vectors u and v are parallel. When you say two vectors are parallel, they could either be on top of each other or they could be parallel like you usually think about, like being two railway tracks. Okay. So both are okay here. Two vectors u and v are parallel if and only if one of these vectors is a scalar multiple of the other vector. Okay. U equal to k times v for a non-zero scalar k. It's kind of clearly written non-zero because if you put k equal to 0, there is nothing interesting going on there. Okay, so k not equal to 0, and again if k equal to 1, we are talking about the same vector. So it's mainly talking about a scaling of a vector that makes it a parallel vector. Okay, so it's something we might use later. So keep that in mind for any given scalar which is non-zero. Okay, two vectors are parallel if one is a scalar multiple of the other. Okay. So this is the end of 1.2 here. Okay. So I told you it's kind of a nice way to just get started, nothing heavy. Okay, but if you need help with any of these, let me know. Okay, during my office hours or send me an email. I can go over any of these in detail, but that's all you need to know from 1.2. If you take the textbook and start reading, there's a lot of things in there. Okay, don't get lost in all that stuff. Will two parallel vectors have the same unit vector? Well, the unit vector is going to be scaled by that. So if you take say 1, 1 and 2, 2, these are parallel vectors. Okay. The unit vector for this is going to be 1 over square root of 2, 1 over square root of 2. And for this one, it's going to be, the magnitude of this is going to be square root of 2 square plus 2 square. That's a square root of 8, which is 2 root 2. So this is 2 over 2 root 2 and 2 over 2 root 2. And if you cancel these, you get the same vector. So if you have parallel vectors, they have the same unit vector in the same direction. If you want it in the opposite direction, you have to put a negative to it. Any other questions? All right, now let's slowly start talking about vector multiplication. So I don't know about today, but in future, if you're in class or online, just have that worksheet handy during lectures so that we could refer to the problems without writing all the details here. At some point today, if I get time, I might start doing that worksheet number 1, but let's see, no hurry. Okay, so section 1.3. I'm going to go a little slow on this one because we need this concept at multiple places later, and I don't want you to be kind of forgetting this over and over. Okay, so this is called the scalar product or the dot product of vectors. Okay, so the fundamental question here is, what do you mean by multiplying two vectors? Okay, whether it's an R2 or R3, do we just multiply the components or just multiply the components crisscross? There are all kinds of possibilities now. What exactly do we mean by multiplying two vectors, say in R2? Okay. So given two vectors, U equal to U1, U2, and V equal to V1, V2 in R2. So let's start slowly there. We define the dot product also called the scalar product. It will be clear why it is called a scalar product. U dot V. So the problem with vectors is that you cannot put that dot without a particular meaning anymore. Okay, usually when you write things like this in ordinary math, you say, oh, that's 2 times 3. Okay. Nobody cares for what kind of multiplication it is, right? If you write two vectors and write a dot in between, it means something very special. Okay. This is a dot product, which is a scalar given by U1 times V1 plus U2 times V2. So what you're doing here is taking a product of the straight components, okay, the x components multiplied with the y components multiplied. Okay. The important thing here is that this is not a vector, right? This is one mistake that you don't want to be caught making several times this semester. Okay, this is not a vector; it's a scalar, and that is why it's called a scalar product. Okay, so it's a conceptually wrong thing to write this as two components like this. Now I will give you a geometric meaning to this a little later. Okay, so what we're doing here is we are taking the straight I mention it this way because we are talking about, if you're just talking about something that is flowing through space, okay, you're just talking about it's going in a straight line. So talking about the straight components, we are not really multiplying U1 with V2 or U2 with V1. Those are cross components. Okay. We're just taking straight components here and adding them together. Because if you think about a fluid that is flowing, for example, you can think about it as just flowing smoothly in a straight line, or kind of creating all kinds of rotational aspects. This is just flowing in a straight line smoothly. Okay, that is what it's doing here. So, example, that U equal to 3, 5 and V equal to -7, 3. Find U dot V. Well, that's a pretty easy thing to do if you know how to multiply numbers and add them. Okay. It's nothing complicated here. U dot V is 3 times -7 plus 5 times 3. And that's -21 plus 15, which is -6. Okay. And it's wrong to write it as -21 comma 15. That is not what it is. Of course, you can define this in R3 as well. Okay, if you could do this with two components, just include an additional component, and that will make it a dot product in R3. So if you have u equal to u1 v1 u1 u2 u3 and v equal to v1 v2 v3 in R3, u dot v is still a number. Okay, it doesn't matter whether you're in R2 or R3 or R4. U dot v is equal to u1 v1 plus u2 v2 plus u3 v3. So it's a very simple process as long as you don't write the answer as a vector, which I keep repeating because every semester I see some students who forget about the fact that this is not a vector. They end up in all kinds of funny situations later. But what exactly is the immediate application? We can talk about fluid flow and all that stuff later. That's more complicated stuff. The easiest application of this concept of a dot product is to find the angle between two vectors. Not just in R2, you can define an angle between two vectors in any dimension, R3, R4. Okay. So let me just draw this triangle here, PQR. So let PQ be the vector u and PR be the vector v. And we are interested in finding this angle here. So theta is the angle between P and Q. Again, it doesn't have to be in R2 or R3, but just for the sake of deriving something, I'm just going to consider this in R2. Okay. That way I don't have to struggle with three-dimensional pictures, which is going to be pretty embarrassing, you will see. Now, I don't know if you have seen this in high school. If A is the length of this line, B is the length of this line, C is the length of this line, and if this angle is theta, okay, there is something called the law of cosines. I've seen that some students have seen this, some students have not. It depends on where you did your high school. The law of cosines says this: c square equal to a square plus b square minus 2ab cosine theta. In particular, if theta is 90 degrees, this becomes equal to the Pythagoras theorem. Okay, so this holds for any triangle. If theta is not 90 degrees, okay, then the length of this side is going to be shorter than what you would expect in a right angle triangle. We're going to make use of that here. Okay, so if this is vector u, this is vector v, then the length, this vector is given by u minus v. Because if it is u plus v, it would have crossed this triangle. Okay, since this is going up like this, this is minus v. That is why we have minus v here. So since I defined my vector as originally going from P to R, that is why you have u plus minus v or u minus v. Okay. So I'm going to make use of the law of cosines here. So that's going to be the length of u minus v whole square equal to, okay, that is my c square, equal to a square plus b square those are my a and b, u and v. Okay. I'm putting absolute value because those are the lengths of the vectors. You cannot write a vector square, that has no meaning. Okay. The length of the vector square, because this is the length of the side. Okay. So it's c square equal to a square plus b square minus 2ab, which is 2 times the length of vector u times the length of vector v times the cosine of the angle theta between those two lines. Now you can expand the left-hand side using your a minus b whole square thing from your previous days, right? So this is going to be the magnitude of u square minus 2 times uv, okay, which is going to be the product of u and v, the dot product of u and v, plus the magnitude of v square. So it's a square minus 2ab plus b square, okay, equal to u square plus v square minus 2 u v cosine theta. Now, if you look at both sides of this equation, you can see there are a bunch of terms which are the same. Okay, so you can cancel the u square and the u square, the length of u square and u square, and similarly you can cancel the length of v square and the length of v square. Okay. And you can also cancel this -2 and -2 from the remaining terms. Once you cancel the other terms, you can then cancel the -2 and -2. Okay, not at the beginning, right? So what you have then is that you have u dot v equal to this block of terms here. This is probably the takeaway from today's lecture. Okay, it tells you something, quick analytic formula for finding the angle between the two vectors if you know their lengths or their magnitudes. Okay. So if you continue from that line there, you get, don't forget you have canceled the -2's, so you get u dot v equal to the magnitude of u times the magnitude of v times cosine theta. Okay. Those are the only terms remaining there. See that? And since we are interested in theta, cosine theta is equal to u dot v divided by the magnitude of u times magnitude of v. Now, the first time you look at it, it might look very bizarre because you are dividing vectors. What does it mean? Okay, this is where you should keep in mind that the dot product is a number. This is a number. That is a number. Okay, so just dividing a number by two other numbers. So there is nothing unusual going on here. Right? So this is the cosine of the angle, so theta equal to cosine inverse of u dot v divided by the magnitude of u times the magnitude of v. We are not doing calculus yet. Okay, we are just doing simple vectors and lines and things. So the measurement of this angle should be still in degrees, not in radians. Okay. Once we switch to calculus, then we will start talking about radian measure of the angle and so on. So this will be some amount of, say, 30 degrees or 45 degrees, depending on what the number comes out to. Okay. But then how is that useful? If you are given u and v in terms of the components, you know how to find u dot v. So if u equal to u1, u2, and v equal to, and we are making use of that picture from R2, so I have to still maintain just two components for now. Okay. Then you know that u dot v is just what we did earlier. It's going to be u1 v1 plus u2 v2. Okay. These are numbers, right? So if we now go back to our expression for theta, this is the cosine inverse of u1 v1 plus u2 v2 divided by this magnitude of u1, which is the square root of magnitude of u, which is the square root of u1 square plus v2 square, times the magnitude of v, which is the square root of v1 square plus v2 square. Okay, that quantity there. Okay. That is a number. So if you take the arc cosine or the inverse cosine, you'll get an angle in degrees that is going to be the angle between the two vectors. the beauty of this is that you can extend this to any dimensions. If you want to find the angle between two vectors in R3 or R4 or R5, the same concept. Okay. So that's the nice thing about building this in R2. Because of the way the dot product behaves, it's just the component-wise products being added together. Okay, there is no limit to how many of these you can add at a time. So if you have U equal to U1, U2, U3, and V equal to V1, V2, V3 in R3, all you're doing is just expanding that and just accounting for the third component or the third component of these two vectors here. So theta would be the sine inverse of U1 V1 plus U2 V2 plus U3 V3 divided by the magnitude of U times the magnitude of V. That's still a number. Okay, so it doesn't matter how far you can keep on extending this in terms of whether you are in R2 or R3, you'll get an answer somehow. Right? All right, so that is probably the most important thing you learned today, okay, to find the angle between two vectors if you know the two components or the components of the two vectors. You don't need to know the derivation or anything. I do this just in case somebody is curious. What we need is really the result here. Okay. I don't ask derivations on tests. So what I'll do now is take the first problem from the worksheet number 1 and do that, and then we'll do the remaining ones tomorrow. Before I do that, do you have any questions? I forgot to ask that. Any conceptual questions about dot product or angle between two vectors? All right. If you, I don't know if I'll just write the question down today. Okay, so we go to modules and then worksheet number 1. So by the end of the semester, we'll have around 14 worksheets, depending on how I divide the material down. Okay. Find the dot product of the following. Find the dot product of 1, -2, 4, and 2, 1, 3. And let's also add an additional part to it, find the angle theta between the two. This is actually not in the worksheet, so it's kind of a extra question. Just for convenience sakes, you can call this as U and V. Okay. Is that okay? Any objections in the classroom? If you object, raise your hand to that answer. Okay, now people online, any objections? There are 3 objections in the classroom. Let me see if people online agree with this or not. Yes, you need to add them together. This is wrong, okay, because dot product is not a vector, it's a scalar. It should be 2 minus 2 plus 12. I'll be tempting you like this a lot during the semester. So. All right, the magnitude of u is the square root of 1 square plus negative 2 square. Sometimes students forget to square it. You have to take each component, square it, and then add it. Plus 16. That's the square root of 21, if my addition is correct. And magnitude of v is the square root of 2 square plus 1 square plus 3 square, which is the square root of 14. Good. So we have all the ingredients you need to find cosine of theta equal to 12 over the square root of 21 times square root of 14. So I don't know if you have a calculator, can you tell me what this number is? Just cosine of theta for now, and then we'll take the inverse cosine. $45.58. Can you tell me what this number was here? 0.69. Okay, so theta would be the arc cosine of the inverse cosine of 0.69, which is around 46 degrees, right? Again, I don't get really excited saying more decimal places. Okay, so yeah, so something that is reasonably close enough should be sufficient for these kinds of problems. Okay. As long as you don't approximate 0.69 to 1 or something, I'm okay. Okay. All right, so I think I'll stop there for today. We will do the remaining worksheet 1 problems tomorrow, and then start talking about other exciting things. So in the meantime, please, if you have not done the survey to take your weekly quizzes, please do it. All right. Thank you. And have a nice day. Yeah. This week it will be based on worksheet number 1. I think I've written it there. So worksheet number 1 and 2, I think. Yeah. I've written it in one of the worksheets, what it is. All right. Thank you very much, everyone. I'll see you tomorrow. I'm going to stop recording.